Hello everyone and welcome. आज के सबक में we are going to uncover the absolute fundamental building blocks of, well, literally all matter. Welcome to this explainer on Class 9 Chemistry, specifically Chapter 2, where we're going to decode the structure of the atom. You know, if you look around you right now, everything you see, touch, and breathe is built from exactly what we're about to discuss. It's just a completely fascinating journey into the microscopic world, so let's get started.
Okay, let's dive right into this. Here is our roadmap for today. We'll start with the atom and its particles, move into atomic and mass number, look at electronic configuration, figure out what isotopes are, discuss the formation of ions, and finish up with a quick review of important questions.
Section 1. The atom and its particles.
So, I want you to think of the atom as the universe's ultimate construction kit. The actual definition of an atom is the smallest particle of matter that retains all the chemical properties of an element. Let's make that a bit more concrete. Imagine you take a solid chunk of pure gold and you just keep cutting it in half over and over again. Eventually, you're going to reach a point where you literally cannot divide it anymore without losing the actual goldness of it. That absolute smallest essential piece that still acts and behaves exactly like gold, that right there is an atom. Now, what's really interesting about this slide is what happens when we break open this tiny atom to look at the three fundamental pieces of our kit. First up is the proton. It carries a positive charge. It sits right in the dead center of the atom, which we call the nucleus, and it has a mass of about 1 atomic mass unit. Next, we have the neutron. This particle has absolutely no charge. It's totally neutral. It also hangs out right there in the nucleus next to the protons, and it weighs exactly the same as a proton. And finally, the electron. This one has a negative charge, but it actually doesn't live in the nucleus. Instead, it races around the outside in specific paths called shells, and its mass is so incredibly low it barely even registers.
Section 2. Atomic and mass number.
So now that we know the pieces, how does nature actually keep track of its inventory? Well, it all comes down to these two crucial terms. On the left, we have the atomic number. This is simply the total number of protons in an element. You can really think of it as the ultimate ID badge of the atom. On the right, we have the mass number. This is the combined total of the protons and the neutrons. Remember how we said electrons are just too light to really matter for weight? That's exactly why, to find the mass number, you only account for the heavy particles sitting tightly together in the nucleus. So mass simply equals protons plus neutrons. Let's look at this in practice with a real example. The number 6. This is the atomic number of carbon. And I really want to point out that this specific number is the absolute identifier. If you have some mystery atom and you peer into its nucleus and count exactly 6 protons, you are strictly dealing with carbon. No exceptions whatsoever. 6 protons always means carbon. But what if we add 2 more protons to that same nucleus? We arrive at the number 8. This is the atomic number of oxygen. Building on our previous point, this shows how changing just this one foundational number completely changes the element's identity. I mean, we've gone from the solid dark soot of carbon to the invisible life-giving gas of oxygen just by changing the atomic number from 6 to 8.
Section 3. Electronic configuration. Okay, let's move to this and see how it builds. I want you to think of electronic configuration as a very strict seating arrangement at a concert. Electrons can't just float wherever they want around the nucleus. They have assigned rows or shells they literally must occupy. And the rule is, you always fill the inner seats first before moving to the outer ones. Take sodium, for example, which has an atomic number of 11, meaning we have 11 electrons to seat. It's arranged perfectly as 2 in the first shell, 8 in the second, and then just 1 left over in the third shell. Magnesium has 12 electrons, so its arrangement naturally goes 2, 8, and 2. It's this beautiful, highly logical progression of completely filling the inside before moving to the outside.
Section 4. What are isotopes? So we know that changing the proton count changes the element entirely, right? But what happens when nature slightly tweaks the recipe, keeping the core identity exactly the same, but altering the overall weight? Well, that specific scenario gives us isotopes. By definition, these are atoms of the same element that have the exact same atomic number but a completely different mass number. Because the atomic number is the same, the proton count strictly stays the same, which means it is absolutely still the exact same element. However, the neutron count fluctuates, which either adds or removes overall weight from the atom.
And this brilliantly illustrates the concept in nature. Look at hydrogen. It naturally exists in these 3 distinct versions, or kind of like flavors. Hydrogen 1 has just a single proton. Hydrogen 2 keeps that 1 proton, but adds a neutron, making it heavier. And then hydrogen 3 adds yet another neutron. They all have one proton, so chemically they all act exactly like hydrogen, but they vary entirely in their physical mass.
Section 5. Formation of ions.
Up until now, we've only discussed neutral atoms, but in reality, atoms act a lot like eager traders in a super busy market. They are constantly looking to gain or lose those outermost electrons to achieve a full, totally stable outer shell. And when they make these trades, they become ions. A positive ion, also known as a cation, is formed when an atom loses an electron. A negative ion, or anion, is formed when an atom gains an electron. I really want to emphasize the fascinating trade-off here. Remember that electrons inherently carry a negative charge. Therefore, losing a negative piece of yourself actually results in a positive charge overall. And conversely, gaining an extra negative electron makes your total charge negative.
Section 6. Review of important questions.
We have covered some truly incredible ground today. So the crucial point is consolidating all this new knowledge with a quick, rapid-fire checklist designed specifically to prep you for your exams. Can you confidently answer these core questions? 1. What is an atom? 2. What are the key differences between a proton, neutron, and electron? 3. Can you explain atomic versus mass number? 4. What are isotopes? And 5. What is electronic configuration? I want to encourage you right now, if you can answer these exact questions without looking at your notes, you have successfully mastered Chapter 2. You've done the hard work, for sure. I want to conclude this explainer with a highly provocative thought for you to just kind of chew on. If every single object in the universe, the phone in your hand, the trees outside, and literally even your own body is built from the exact same 3 fundamental particles, what truly makes you different from a star? It all comes down to the miraculous, invisible architecture of the atom. Thank you so much for joining me in today's lesson. If you found this helpful, please make sure to like, share, and subscribe so we can keep making these explainers. Al Hafiz, stay safe, and I will see you in the next one.